Welcome everybody for this ISCS IIT Combinator Gravitational-wave seminar series. We have been able to continue and we are very happy for that. So today we have Aaron Hurd with us, who is currently a Philippe Mayer Junior Research Chair at École Normale in Paris. So we are very happy that he has kindly agreed to give this seminar and he is going to talk about numerical relativity and effective field theories of gravity. And your work, please.
Yeah, thanks for the invitation, and also thanks to everyone who's joining for the interest. I wanted to sort of summarize today what I think is exciting because it brings us into a position where we can do what the title of the talk is. We can actually start to do numerical relativity, fully fledged as in general relativity, in modified theories of gravity. And in particular, I will focus on effective field theories of gravity because I think it's a nice framework that in principle should encompass all possible modifications, at least the onset of all possible modifications. And then sort of the goal of this whole program is to be able to perform numerical relativity simulations and then extract waveforms such as the one that you're already seeing here on top. And so what I'm going to go through today, hopefully with enough time, I want to sort of introduce exactly what I mean by effective field theory, because there's different types of effective field theories that people set up, even just in the gravitational wave context, and I want to be specific what I actually mean. Then I want to take you through some, it might be, the part two might be a little formal. There's some mathematical properties which I want to introduce, which basically lead us to be able to phrase the system of equations, right? Think of GR having the Einstein equations, and this beyond GR theory or the effective field theory has some more complicated evolution equations. And they have to be phrased in a certain way such that you can even start to perform numerical simulations, and that goes by the name of well-posedness. And by now, I think we understand quite a lot about well-posedness, and in particular, there was a paper this year by Paul Figueras, Aaron Kovac, and myself, which I think is really a step forward in making this work more generally. And then in part three, I'll show you some work which I've previously already been working on and which has also informed how we lead the proof here. Which is in a specific truncation of the effective field theory, where we then actually already have performed full nonlinear simulations as the one with waveform that you're seeing here. And then during the talk, some of you may or may not start to wonder about ghosts, whereby I really mean Ostrogradsky ghosts, so wrong sign kinetic terms. Because the equations of motion that we will render well posed, they will be higher derivative equations of motion, so higher time derivatives, and therefore they will generically contain ghosts. And there's a bit of confusion, I think, out there, what it means that there is a ghost, what the ghost instability really is, and in particular the relation between the ghost instability and well-posedness. And so I'll, if we have time in the end, I'm happy to clarify that, or otherwise answer questions on that. Regarding questions also, anytime you have questions in between, feel free to jump in. So, because I think it's much more reasonable if we ask them as soon as possible. And it's also more fun for me then. All right. So with that, let us get started. So as I said, I wanted to summarize what I mean by effective field theories. And so first, fully general, the effective field theory framework, probably most of you have been in contact with some effective field theory by now. It's basically used all over physics, from the standard model to cosmology to very, very applied infrared physics as well. You assume a given field content that typically you know from infrared, right? So in the case of general relativity, that would be the metric. And I'm putting a star here because that's the most tricky assumption. And you will see later on that one can assume additional light fields and then one slightly switches to a different EFT. One assumes infrared symmetries, and I will not mess with the symmetries at all. So in our case, in the case of gravity, that's just the Lorentz invariance. the full diffeomorphism group, they will always be left intact and I will not break any part of it. And then you have to come up with an expansion scheme, typically tied to a physical scale in the problem. And in our case, we will actually perform a mixed expansion in both curvature, so really local curvature in the spacetime, and derivatives. So basically just in dimension that you can write down in natural units of any possible operator. And then when you fix these things, then effective field theory tells you that you should go to the level of the action in our case and expand your theory or your action in all possible operators that you can write down. And so that's just the framework. And the nice thing about it is that within the regime of validity, so if you check that you're in a regime where the next operators are always small and you assume at least some apparent convergence of this series of perturbations in the action, then there are very good arguments and in fact lots of examples that any unknown UV physics can then be captured in the coefficients of this effective field theory. And so really at that point I don't need to specify what beyond GR physics I'm considering. I'm really considering the onset of any possible beyond GR physics, any heavy modes that might be around and come in at the scale of the binary system that we want to investigate in the end. So this is nice because I think it introduces some form of rules to modified gravity, right? Because now not everything goes, because otherwise I would have to decide exactly what light fields I mean. Here I really just do this expansion systematically. And so let's start to do that for the case of gravity. So I start with the lowest possible term, or actually even lower, that would be an L0, which would be the cosmological constant. But let's forget about the cosmological constant for now. Then at the level of one dimension in curvature, one curvature, 2 dimension, I can write down the Riemann tensor itself, or in this case, I need to contract all the indices to maintain Lorentz symmetry. So I'm writing down only the Ricci scalar. That's the only object that you can write down in 4 dimensions. And I'm dressing it with some function to make the to get the appropriate units, right? To make the action dimensionless. So that in that case, I'm picking here the Planck mass, but you could pick some other length scale to introduce into the problem. And then at the next order, you can write down more invariants, right? You can write down, in this case, I'm writing down the Ricci scalar and some contraction of the Ricci tensor. And actually, these are the only 2 invariants after you perform these steps here. So you really apply all the possible index symmetries of your Riemann tensor. You use all the geometric identities that you have. And in this case, very importantly, you use 4-dimensional specific identities. Here, for instance, the Gauss-Bonnet identity. Otherwise, you could also write down a Riemann squared, right? You would probably expect that there's a Riemann tensor invariant. But with this third point, you can rephrase that invariant into the ones which are shown here, up to boundary terms. And this sort of scheme, there's actually lots of work performed in this area, and it's systematically known how to do that even to high order. I've put, I think, the most important references here for you. And even this here is even, there's even a Mathematica package that basically does that step for you. So that's why going to a higher order, even though it becomes much more complex, is feasible. So you can go to the next order in cubic. Now I'm writing down terms with 3 curvatures, and I'm writing down all possible in contractions. And once you've again performed all these symmetry reduction steps, these are the only independent terms which remain. I think eight of them. And then you go on, and you can go on arbitrarily high. Here I'm stopping to write down all of them because I think it's more than 10 at the quartic level. But that's what it is. That's how you would, that's actually the complexity, the index complexity of such an effective field theory expansion of gravity. All right, so this is nice, and all of sorry, yeah, there's
Yeah, I mean,
Sayantan.
you actually asked, can I ask a question in between?
Yeah,
Yeah.
sure.
Yeah, so I am asking that why are you taking well curvature square? Because if you decompose the well curvature in the Riemann tensor, it would still give a like Gauss-Bonnet term, right? In 4 dimension, it would, like if I take C ABCD and C ABCD, if I break it into R ABCD, R ABCD, and this, I can still neglect it as a boundary term. So that's what I'm asking, why there is a C square coming. I mean,
If
because it would
if
end with the Gauss. Yeah.
if there's no further curvature tensors involved. So you're right that like here at the level of the quadratic invariance, if I'm writing down CABCD, CABCD, then that's exactly what you're using. You can translate it into the Riemann and then into a Gauss-Bonnet, and you can recast it into these. But the whole story with the boundary terms is no longer true if there's an additional invariant here, because you would have to partially integrate and then you would get derivatives of R, and then you would sort of mix it into other invariants.
Oh, okay. Sorry, I didn't saw the R. Thank you, sir. Okay.
Jose?
Yes, one
Yeah.
question. Are you going to say something about the fact that you are choosing M Planck as the scale for the corrections? Let's say you could have a different scale for the.
That's absolutely right. And you can really just think of this as setting my units. And if you want, you can put some L. And indeed, like if I think of physics that enters, for instance, at the scale of some astrophysical black hole, the relevant scale would be the Schwarzschild radius of that respective black hole, or the horizon curvature of the respective black hole. And then I think it's much more reasonable to not put the Planck scale here, but to put that scale there. That just means that if I put the Planck scale, then I get all these terms until they become relevant for the respective problem. They would have to become very large.
Okay.
All right. So all of what I'm saying here is before field redefinitions. What do I mean by field redefinitions? I mean something like that. You take the metric and you transform it to a different metric, which is just the metric that you had before, plus some other terms which come with curvature dressed. So in this case, I can build, since the metric has two indices, I can either put a scalar or some object with two indices. That is what is known as a field redefinition. And at least perturbatively, this field redefinition is completely invertible, and it should, people expect that at least if the physics remains close to where you started out, this field redefinition should leave the physics independent. I think this is something that we should be a little careful with, because one can do, even with that type of field redefinition, it's not clear to me whether one changes the physics or not, but it's common practice in effective field theories, at least when remaining perturbatively close throughout the manifold, to perform these field redefinitions. So if you perform these field redefinitions, you can already see that I can now use here in term of x, I can use the Ricci scalar, and in terms of xab, I can use the Ricci tensor. And that means that I can sort of reshuffle terms here into others, and I can in fact remove all the terms which contain a Ricci tensor or a Ricci scalar by such a field redefinition, perturbatively. So I would be trading these terms order by order for terms of the next higher order. Yeah, sorry, there's another question.
Yeah, the x variables which are there, x or xab, are they also functions of GABs or some completely independent?
So here I'm not thinking, I mean, of course, like they are functions of GAB, for instance, through the Ricci curvature. Yes, that's right.
So capital X as well as xab do depend on the metric and only on the metric and its derivative, of course.
In the end, the only field that I'm considering is the metric. Yes, exactly.
So including X. Okay.
Yes.
Thank you. Yeah.
So importantly is perturbatively with such a field redefinition. If you consider everything in the perturbative regime, then you're moving sort of, instead of these terms, you're moving the respective alpha zero coefficient to the next order of the effective field theory, and then you would perform it again at that level and move it to the quartic, and at the quartic move it to the fifth order. And thereby you're sort of shuffling all possible terms to higher order in your effective field theory expansion. So that means that if you trust these field definitions, then the leading order corrections in vacuum EFT expansion around GR would be the cubic ones, and then there would be the quartic ones. And if you're more careful and you maybe, for instance, the boundary condition you're more concerned about, then the leading ones would be the quadratic ones. All right. That's what I mean by the effective field theory. In this case now after field redefinitions. So what will become very important in the talk are these terms that I've marked here, which we have which we've removed by field redefinitions. So part of the terms which we've removed by field redefinitions. And these are important. So they are special in the following sense, because they have the highest number of derivatives acting on a single metric. So, right, because in the Ricci here, there's a metric which already has two derivatives acting on it. So I'm acting on it with two more derivatives. So there's four derivatives acting on a single metric in this type of term. And in all the other ones, there's less derivatives acting on a single metric. And it's already, if you know a little bit about partial differential equations, the terms where the most derivatives act on a single field are the ones which dominate the so-called principal part and are crucial for well-posedness. And so what we are going to do is we're going to reintroduce these terms. You can think of it that if you trust the field redefinition, then you just reintroduce these terms here by another field redefinition with appropriate coefficients. And that will help with well-posedness. If you don't want to consider the field redefinitions, then you just leave these terms in place. All you will have to do in the end is borrow, you will see, one term from the next order of your effective field theory. So it works with and without field redefinitions, actually. All right, so before I go to well-posedness, are there any further questions to this sort of brief introductory part?
So what happens if I, let's say, consider first order variables? There are tetrads and spin connections as well. So then you will put those fields as well, and then you are going to have more terms in the Lagrangian, right? So
yes, I think so. And I haven't ever done that. But probably someone, I guess, has looked at an EFT expansion at the level of tetrads. So I think that if you would keep all the symmetries and you would just rephrase basically the degrees of freedom which are in the metric as degrees of freedom in a tetrad, then I think you should find an equivalent expansion, although I'm not sure it has been done in full glory. But of course, like you can now break different parts of the symmetries, and then you should probably the tetrad can have different components. So it's just a different EFT, I think.
okay, thank you.
But yeah, here I'm not doing any of this. Yeah.
Alan, so here. So this is for pure gravity, right? So
that's right.
If we have another matter field like a F mu nu or A mu or something, would you consider non-minimal coupled term also as a part of this EFT series?
Yes, very much so. And indeed, so if you would, for instance, the simplest thing that you could look at as an additional field would be a scalar, right? Yeah. And if you added a scalar, then performing this type of field redefinition to get rid of these terms will introduce other terms coupling to the scalar, and that is what is known as Einstein-Dilaton-Gauss-Bonnet. So you introduce two types of invariance between non-minimal couplings between the scalar and the curvature. So then you're in a again, I would say a different class of EFTs, because here I'm not considering an additional scalar field. And you can do the same thing, I think, for vector and for a field density, like an electric field.
Thank you. Thank you.
Sir?
Yeah.
Sorry. May I ask a question?
Yeah, sure.
As a small question, if I were to take this and now linearize about and G bar AB.
Yes.
I can get higher derivative terms of the perturbations, right? Because I'm linearizing, so I'm throwing away all other terms. How much modification does one get? I mean, I can't immediately see it. So if I want to look at, I want to linearize about some background metric that I choose. This entire effective action.
I mean,
So,
of course, you can
so
linearize the equations of motion around the background.
Yeah. That's what I mean. Yeah, that's. I mean, the action will be up to quadratic. Yes. Yeah. Sure. How much is it, I mean, I can't see quickly. I have not tried this. How much will the equations of motion change? Linearized equations of motion.
So if you are in the if you remain within the regime of effective field theory,
yes,
then there will be no additional modes to your perturbations, but still the perturbations can have different character, because of course the nonlinear background, right? It can enter with arbitrary order. So think of, like, in this term, you can pick up the linearized fluctuation from one of the curvature scalars.
Yes.
But then the other two could be evaluated on the background.
Yes. They could vanish.
And so that would change your perturbation equation. So in principle, it can change even the linear perturbations about a curved background. If you're around flat space, it can't.
Yeah. Also, if I look at, say, de Sitter or anti-de Sitter, in that, I think there also it's while invariant.
So exactly. So if you have a while invariant spacetime and all the while scalars vanish, then
so then it will not affect the equation. Okay. Thanks.
Exactly.
Yeah. Thanks.
So there was one question, right? Swan, yeah.
Yes, sir. I have a question. My question is the graviton particles is discovered?
Is it discovered? Was that the question?
Yeah, maybe this can be discussed later.
Yeah, but I think so. For sure, we measure a field which is, like, we measure gravitational waves which are compatible with the interpretation of a metric. Yes. So in that sense, it is discovered. I'm not sure whether you're talking about a quantized graviton, then it becomes much more of a tricky question.
It is discovered or not?
The field, everything that we see is compatible with the interpretation of a graviton field, yes. All right, good. So let's proceed with, I think, a little bit of a mathematical part, but please bear with me. So this is based on actually a kind of old paper, and I really encourage you to go and read it, because it's super nice, by David Noakes from 1983, where really, so I started working on this like 4 years ago or so, because of this paper, because I was surprised, and he actually proves that the quadratic truncation, so the this theory here, which I will call quadratic gravity, has a well-posed initial value problem. And the way that he proves it has sort of eventually now led to this paper here, where we sort of take it to arbitrary order in the effective field theory. So the way that I want to present this today is via so-called Leray weights or Leray weights, which are a method which has also been used by Yvonne Choquet-Brouhat to prove well-posedness in general relativity. And then it has been used by Noakes to prove well-posedness in quadratic gravity. And indeed, you can understand all the higher orders as well in this formalism, which is what I'm going to present today. In the paper here with Paul and Aaron, we use modern methods of proving well-posedness, and in particular, Aaron, which is a different Aaron than me, has a lot of expertise in this and has led this part of the collaboration. All right. So first of all, let me quickly repeat what I mean by a well-posed initial value problem. So you would say that an initial value problem, meaning that I take my space-time and I slice it into 3-dimensional slices and one time direction. I can do that in many different ways, but I do it in some way. Then I put initial data, so I pick the derivatives and the fields depending on the order of my equation on that slice. and I want to evolve it in time. Then the initial value problem is well posed if that solution that I'm obtaining here exists for all future time, is unique, and depends continuously on the initial data. And I put here for all future time, which means that I'm looking for global well-posedness. If I'm just thinking of a small epsilon in future time, then I'm thinking of local well-posedness. And to me, global well-posedness is really something that connects very deeply to obviously hyperbolicity, but also just to whether we can do physics with such a theory. Because think of setting up an experiment. You're setting up an experiment at some time, right? And then you want it to predict the future. So that's exactly what well-posedness tells you. Can you predict the future? And if your theory cannot predict the future, in particular, the future on the relevant timescales of your experiment, then it's a bad theory. And so I think it's underappreciated that this might be really a consistency criterion for theories that we write down. There's a slight subtlety here because it can happen, and in fact in GR, for instance, it does happen, that a certain formulation, but you find a different formulation for which it is well posed. All right, with that said, that's a physics sort of transgression, but certainly to put anything on a computer, you need the initial value problem to be well posed, simply because as you discretize, if you make the grid spacing smaller and your problem is ill posed, it can happen that as you make your resolution better, so as you put more numerics into the problem, the way that you obtain the solution becomes worse. So you approximate the continuum worse and worse. And so that, of course, means that you cannot really do numerics. So now for general relativity, as I already mentioned a couple of times, Yvonne Choquet-Brouhat, who, by the way, is still alive, which is really cool. I've tried to meet her in Paris. She has proven the formal existence and uniqueness in general relativity. And then it took the development of supercomputers to actually perform simulations, but it's all based on this formal proof of well-posedness. Now, as I said, for quadratic gravity, David Noakes has proved that in 1983. And we have used that by now, myself and Hyun Lim, and then also some other groups have used this to simulate this quadratic gravity theory. And then recently we've extended it to the EFT. Okay, so that's the initial value problem. Yeah.
So in GR also, what happens if there is a Cauchy horizon? I mean, does it create a problem for this well-posedness?
Yeah, so this is the difference between local well-posedness and global well-posedness. And so what I'm interested here is only local well-posedness, and also local well-posedness in the exterior domain of a black hole in the end. And you're right that if you come to a Cauchy horizon, then you lose global well-posedness, which is related to cosmic censorship and all of that. And this is indeed what is the physical question side that I was alluding at here, which I think is really very important, but not so much a problem for numerics, or at least not if you want to look at the exterior of black holes.
So even in GR, the global well-posedness is not true, right? At least at the face of.
Exactly. So global well-posedness on the entire domain, including the interior of black holes, breaks down. It's not true. Exactly.
Thank you.
All right. So the mathematical theorem that we will be using, and in fact already Choquet-Brouhat used, is very nicely introduced in this textbook of her and DeWitt Moret. And it's a theorem by Leray, and it talks about Leray weights. So what we will do is we will take the system of partial differential equations, which I will call E, and respective variables V. So we use second order equations, and we use the same number of equations and the same number of variables, and we label them by an I. And then the principal part, which is just the part with the highest number of derivatives acting on a single field, that can be diagonalized if there exist positive integers which fulfill certain conditions. That's what Leray proves. And then one can use another theorem to say that if such a diagonalized system exists, then you can, phrasing it in the right way, obtain a well-posed initial value problem. So this really, if we can diagonalize, we're basically done, because there exist math proofs for the rest of the story. It still depends on gauge, but this subtlety, let's not discuss it today. So the two conditions are basically telling you the prescription of how to diagonalize the system. So first, you focus on the variables which contribute to their own evolution equation, which means that the I is supposed to be the same. And then you can find a set of integers for which this combination, Si minus Ti, characterizes the order of the respective equation. And if you then look at cross terms between the different variables, so for j different than I, then they should always be of lower order than the ones which were not cross terms. That's the formal definition. And I appreciate that it's much easier to sort of go through an example. So I sort of tried to come up with the simplest example that I could come up, which gives a prescription to then diagonalize the principal part. And here's the example that I want to discuss. So it's really just a system of two partial differential equations. They have box operators, which are wave operators. Really, I mean just dt squared minus some spatial part dx squared, depending on your signature. They both have this type of thing, and if they only had the left-hand side term, they would already be diagonal, right? Because the box only acts on the variable u itself. It doesn't mix the v into that system of equations. Now I've put this particular term here on the right-hand side, which is also of second order, which means that the system here is not immediately in diagonal form in the principal part. So it's not of quasi-diagonal form. But you can find these Leray weights here. So, and now you can check the conditions from the previous slide. You can check that if you take 2 minus 0, you get 2, which is exactly the order of this equation, right? Because the derivatives on u are second order. Similarly, if you take 3 minus 1, you get 2, which is the order of this equation. There's second derivatives on v. And if you perform cross analysis, you take 2 minus 1, which is 1. Then 1 is larger than 0, which is the order with which v contributes to the first equation. And vice versa, 3 minus 0 is 3, which is larger than 2, which is the derivative order with which here the dt acts on the u, so on the other variable in the second equation. So in that way, you can understand that these Leray weights tell you that this system of equations should be diagonalizable. Yeah?
Yeah, one short question. So you are considering a system of second order partial differential equations,
Yes.
matrix form.
Yes. Yeah, go ahead.
You could also write in terms of first order system. Why do
That's right. I could do that. And then so actually if you look at the paper with Aaron and Paul, that's what I meant by more modern methods. So there we really write the system as a first order system and analyze the full matrix of the principal part. And so so it's just that here it's a little simpler to understand it in terms of Leray weights, I think.
So right now you're just putting it as a second order equation, matrix partial differential, and then the diagonalization.
Sorry, say again.
So right now you are only considering second order partial differential equations in a matrix form.
That's right.
Yeah.
That's
okay.
right.
Yeah.
And it's important actually that I'm only considering second order equations. I think the Leray theorem is not necessarily true for higher order than second order.
Okay, but any system I can always put in this form, right? Arbitrary derivative, I can increase number of variables and put it in that.
So certainly the systems that you will see in the higher derivative theories, you can recast them in larger systems of second order equations. Exactly. I'm not sure whether you can do that with any system of equations, but yeah.
Okay. Okay, fine. Thank you.
So in this particular example, you can now use explicit diagonalization. And that is basically what the Leray weights tell you. You can take one extra derivative of your first equation, So I'm introducing a dt of u, which I just label as a new variable u dot, right? And then the first equation is just box u dot dtv, taking another derivative of that equation and considering flat space and just commuting all the derivatives. And then the second equation loses one order on the right-hand side. And that's exactly what is possible because of the Leray weights. And this one now has a diagonal principal part. And that's exactly sort of how the proof of Leray works, that if you have such a system of integers, then you can do that. So the integers, in the next slides, I will put them above the equations because that's easier to sort of keep track of. Then the difference between these two integers always must be 2 because we're dealing with second order equations. And then you can have different ones of these sets above the different equations. All right, so let's start looking at gravity. Let's start looking at general relativity. And I'm going to harmonic gauge, which makes the system actually already well posed, by which I mean that I'm considering a gauge potential, which is just the contracted Christoffel symbol. And then you can write actually the Ricci curvature as this expression, where importantly this left out term only has first order derivatives of the metric, so it doesn't contribute to the principal part. And if I now pick a gauge in which that f vanishes or is constant, then also this term here does not contribute. And then in harmonic gauges, the Ricci curvature is just a wave equation for the metric. And so if you think of the Einstein equation in vacuum just being Ricci curvature equals 0, it really reduces to the principal part of a wave equation in harmonic gauge. And so it's already in the form that we were seeking. It's already in a diagonalized form. So in harmonic gauge, the Einstein equations are already of wave-like form, and then you're basically done. So here the real insight from Choquet-Brouillard is on the gauge part, to make sure that you're picking harmonic gauge such that the system is in quasi-linear form. Yeah?
Yeah, the box is the standard Minkowski box, right?
In this, it's the standard. Well, it doesn't have to be Minkowski. It's the standard covariant box operator.
But covariant derivatives of the metric will be 0, no?
Wait, sorry. Yeah, you're absolutely right. Yeah, you're right. In this equation here, in this specific equation, yeah. Actually, yeah, I should have put this as a box bar. You're right. Yeah.
Yeah. Okay. Thanks.
Absolutely. Okay. Thanks. So as I said, that's already in wave-like form. Now I'm going to take you through the quadratic gravity example, which is basically a brief summary of how Noakes proves that. So the first thing is exactly what we discussed, that if you have the set of higher derivative equations, in this case, if you vary this Lagrangian or the respective action, you can look at Stella's paper, you obtain a fourth order equation of motion, right? And now I can reduce that fourth order equation to second order. And in that step, it's very useful to understand the degrees of freedom, which Stella already did, and Noakes uses the linearized degrees of freedom to cast that fourth order system of equations to a larger second order system of equations, which then has the following degrees of freedom. It has the massless spin 2 graviton. It has a massive scalar, which is basically the Ricci scalar, and it has a massive spin 2 particle, which is basically the traceless Ricci tensor. And you can count the numbers of free data that is obtained in these variables, and it matches these degrees of freedom. And this particle is actually a ghost. You can also see that if you go through recasting the action into an action for these fields, then you can see, for instance, basically by an Ostrogradsky analysis, that the kinetic term comes with the wrong sign. Or if you go to the equivalent Hamiltonian, you can also see that. But all right, so this is now a second order system of equations. And indeed, you can find, so first of all, if you get rid of this operator here, for equal masses, so if these two masses are the same, then this off-diagonal term vanishes, And all the other terms are lower order anyways, so then it's already of wave-like form. But Noakes realized that even if this term here is present, so for the generic couplings, you can still find this set of Leray indices, which again have the right structure, and you can diagonalize the system. And in his paper, he actually does the specific, the explicit diagonalization subsequently to finding these integers. So even for unequal masses, you can still find suitable Leray weights, and the system should still be well posed. So it admits Leray weights for its second-order field equations. And just to point out, we will use this fact of equal masses in the following at higher order. So now let's look at the cubic case. If you go to the cubic case, and I've now introduced these terms here, which I mentioned in the beginning are the terms which lead in terms of number of derivatives acting on a single field. These are what we call in the paper regularizing terms, because they are important to be able to make the theory well posed. If you would omit those, just this theory, it's not obvious at all that it has a well posed initial value problem. And in fact, for now, I don't think anyone has found one. Okay, so but with these terms, you can again take the equations of motion. They are now sixth order, and you can reduce them to a second order form by introducing yet more variables. So now you basically are starting to see a tower of massive fields. So you have the metric, you have some while equations, which are really just geometrical. They don't introduce additional initial data. Then you have again a massive scalar and another copy of a massive scalar and a massive tensor and another copy of a massive tensor. And all of this is diagonal, except again for this offending term here, which is very similar to the one which you saw for the Noakes quadratic gravity case. Yeah?
Yeah, in the quadratic gravity case, the fact that these are ghost terms doesn't affect because you said it's still well posed, but they are still ghost, and that is independent. I mean, it doesn't affect the well posedness problem.
It doesn't, and I think this is really something that is somehow has emerged through unsecured knowledge that a lot of people are of the opinion that something that has a ghost, an Ostrogradsky ghost, cannot be well posed. That is not true. It's just not correct. And you can write down scalar field systems, and if I have time in the end, I think I can say a little bit on why.
Sure. Okay, good. Thanks.
But in fact, I think you can basically see the systems that I'm talking about today as examples of that, because there are clearly ghosts and they are clearly well posed, and I will show you simulations in the end as well. So here, if I now pick for this highest equation in the tower of massive modes, if I pick the masses to be equal again, which in these coefficients here means that I'm picking alpha 1 equals 2 beta 1, then this part of the equation vanishes. And then you can see that you can again assign suitable Leray weights to make this whole system of equations, including the wild curvature, quasi-diagonal, of quasi-linear diagonal form. So this really relies on picking these masses in that way. And that means that I either have to use field redefinitions, or I have to use yet another order in the EFT and add the respective regularizing equation to the equation of motion. But then you admit wave-like second-order field equations, and also the cubic theory has a well-posed initial value problem. And now I've already talked about this tower of equations. It's very suggestive now that you can do this to any order. And indeed, we were able to inductively prove this at any order in the EFT, as long as you introduce these respective terms with box to the power of k. At any order k, you can regularize the EFT. So in fact, you can regularize this regularizing action itself. Sorry, you can show that the regularizing effective action itself is well posed. And then adding lower order terms just doesn't change the character of the principal part. So here I'm now writing down basically the same thing as on the previous slide, just adding a tower of k different ones in between, and then there's the highest order term here. I've already picked the alpha n equals 2 beta n here, where n really only needs to be the highest k. And then again, you can pick Leray weights like this. And then again, this admits quasi-linear form, and it's therefore will have a well-posed initial value problem. For the complete proof, also in modern language, you can look at the paper if you want to. All of this is not altered if you add to the action lower order terms, right? So for instance, in the cubic case, without this term which we were actually interested in simulating, this part would be well posed if you pick alpha 1 equals 2 beta 1. And then adding that just adds lower order terms to this set of equations, so it doesn't affect the well posedness. And the same thing proceeds at higher order in the EFT. All right, so with that, all of these regularized EFT field equations will admit second order well-posed form. And so indeed, GR was well-posed by Choquet-Bruhat, the second order form was well-posed by Noakes, and then now the whole tower of EFTs in the regime of EFT is also well-posed. And the last thing that I want to highlight is that really the proof, the way that basically relies on you dominating the principal part with highest derivative terms. So while I've talked a lot about the effective field theory as what I think is the most interesting, or potentially at least one of the most interesting applications, the fact that you can thereby generate well-posed initial value formulations is completely general. So I think it works also for other field content and so on. All right. So if there's more questions on that part, it's another good point to jump in. Yeah.
When you have the instability, what happens to long-term instability? You had
you're talking about,
you're
talking about the ghost now, right?
Yes. So it is unstable basically. I mean, that's what the usual interpretation of the negative kinetic term is. So that if I were to deviate from the solution will diverge, right? Nearby solutions will diverge. So
yeah,
in fact, the continuity for the long-term evolution.
Yeah, importantly, so when you're talking about that type of instability, you mean a physical instability, right?
Yes.
Here, well-posedness is local well-posedness, at least, so for some time, is concerned with numerical stability, right? Yeah. So it's perfectly possible that you have a system which has a physical instability. Think of, for instance, a tachyon, or think of a pen standing on its tip and falling down. I can go on a computer and I can simulate the pen falling down, at least until it hits the surface of the table. So for that number of time evolution, the pen falling down is perfectly well posed. And I think here it's the same thing, that there might be a physical instability, but even if it is there, we can still find a well-posed initial value problem. Then now the crucial question, of course, with respect to waveforms and with respect to physics is, can we control that instability sufficiently well so that we can extract physics from the problem without having these modes, right? We don't consider the modes, this tower of modes that I've shown you, we don't consider it to be physical in the EFT, right? We would only consider the metric to be physical. So we want all these modes to not be excited. So we have to pick their masses appropriately high. And then I think it's reasonable to think, and in fact, the quadratic gravity case is an example where it seems to work, that you can pick the masses high enough and you will not excite the ghosts.
Okay, so in effect, what you said in the beginning, that for all time will be reduced to interval, we also mentioned that, where
yes.
interval of interest and all that the instabilities will do, ghost instabilities, is to restrict that to some extent, and then depending
Absolutely.
upon what you want to. Okay, good. I understand.
Indeed,
Thanks.
all of this is just local well-posedness. Yes.
Fine. Okay. Thanks.
So, and Sudipto, so
yeah,
one question. So, if we go beyond the regime of the effective field theories, I mean, even let us not touch the notion of ghost, even the well-posedness. What can we say from this proof?
Yeah, this is a very good question. And so if you go beyond the regime of the EFT, I think you will excite the ghost. And now you said forget about the ghost, so I will not care about there potentially being a ghost instability. It's still, I think this means that the character of the equations in the, so let's call the, if I take these equations or equations that follow from such an action, and I take them at face value, I don't care anymore about an EFT cutoff. Let's call it the soft UV completion or something like that. I think it means that the equations of motion in the soft UV completion of that type will always remain of wave-like form. But we haven't strictly proven that.
Because you only have to look at the highest order, right?
Exactly, yeah.
Thank you.
All right, so in the last part, I want to quickly take you through an example of actual numerical simulations. And really just for how this evolved in time, I will use the quadratic order, even though we understand already from the first part of the talk that you can remove these terms by field redefinitions as long as you remain perturbatively close to a general relativity vacuum. And you will see that coming in the talk, you will see that resurfacing in this part. But since we had the proof by Noakes already when I started working on this in 2020 or 2021, we just wanted to simulate that theory because it was well posed. And then meanwhile simulating that, we were able to use the same methods to sort of prove a larger class where we're starting to work on simulations right now. Okay, so simulations only in the quadratic theory. So I'm looking at this action. And on the computer doesn't care about the cutoff of the effective field theory. So I think the most faithful interpretation of the simulations is in the soft UV completion. So if I take all these modes here seriously. So in some sense, I should also see what happens to the ghost, whether I excite the ghost on that initial data or not, and so on. So you can think of this whole thing as a benchmark model to then proceed to cubic and quartic terms. You can think of it as preparing for non-vacuum simulations, so for neutron star binaries, because then we surely cannot perform the field redefinitions. Or you can think of it as a fundamental theory, which is, of course, then you have to, at some point, worry about the ghost. All right. So what I want to take you through is I want to now show you that I gave all this mathematical introduction about well-posedness. Now, can I actually give you a stable numerical evolution? And the answer is yes. And then I want to look at isolated black holes and about stability and transitions, and then finally show you the waveform that I showed you in the beginning already. Okay, let's be very quick on that because I'm starting to run out of time. Here I want to thank Hyun Lim, my collaborator in Los Alamos, who's really the expert on the numerical relativity part. I'm learning a lot on numerical relativity. This is the code that we're using. Importantly, for the next slides, it uses fourth order finite differencing, both in time and in space. And here you've seen a merger simulation. There's a lot of adaptive mesh refinement, which you see here. A lot of technical things going into that, a lot of work. This is what you see here now is an example of that the code actually behaves perfectly well until the very end of the simulation. You see the constraint here, the Hamiltonian constraint, which means that I'm really plotting the difference to the initial Hamiltonian, and of course the Hamiltonian should be a conserved quantity, so that difference should be small. In the beginning you see the constraint being damped, and then the constraint remains at a given level depending on the noise in the initial data. That's a so-called convergence test that you see here, And similarly, we can see that we recover the fourth order that I said in finite differencing in space and evolution in time. We recover actually fourth order convergence as you refine the simulation resolution. And that's sort of I said in the beginning that if you have an ill-posed problem, if you go to smaller resolution, your numerics becomes worse. That's somehow telling you that that's not the case here. Yeah?
Yeah. This noise term you mentioned, so is it that the initial data is made noisy by adding some random variables?
Exactly. So we had I discussed these the Ricci tensor, and we rephrase all of that in first order variables, and on all of these first order variables we add random noise. I think physically you can think of this as being just arbitrary perturbations of the space-time at that level here.
Yeah. Fine. Okay.
All right, so it's numerically stable. And now the next thing we did is look at single black holes, because at that point we were very, very careful about the ghost, exactly because of the confusion that I mentioned. So first of all, you can also understand the single solutions and their perturbations, we mentioned that already, by linearizing and looking at analytically at the linearized regime. And so here I've drawn you the two main, or the two only asymptotically flat black hole branches, so they have a horizon and are asymptotically flat in this theory of quadratic gravity, and I'm visualizing them as a function of their horizon radius rg and of the asymptotic mass m. So think of this as the asymptotic Schwarzschild mass, and m2 is, just to remind, this is the m2 was the mass of the ghost, of the spin 2 heavy particle. So I'm just rescaling this here so that the plot applies to any value of m2. Now you can understand that the diagonal line here is just the Schwarzschild solution, because Rg equals 2m on everywhere on this solution. So it's basically parameterized just by its asymptotic mass. This also tells you that the Schwarzschild solution is a solution to quadratic gravity as well, and in fact any vacuum solution of GR, even a complicated binary merger, as long as it's a merger in vacuum, is a solution to that theory. The non-trivial part is whether it's a stable solution to that theory. So now there's a different branch of black holes as well. So here it's a single black hole again. It has a very different horizon behavior, and it's really physically very weird in the sense that if you increase the asymptotic mass, so if you go up in the plot, the horizon shrinks. So that, I think, is intuitively shows you the ghost character of the theory. So if you make, or vice versa, if you make the horizon larger, at some point you make the asymptotic mass negative. All right, so we were interested here in this paper about the stability, the linear stability on these branches, and there have been some previous work on that. The basic upshot, just let me quickly finish that, is that on this Schwarzschild branch, there's an instability which is signaled by a positive part of the respective mode, the positive growth of the exponential growth of the respective mode. It occurs only for small black holes. And also in the other branch, the instability only occurs for small black holes. So black holes seem to be stable if they are sufficiently large and unstable if they are sufficiently small. Yeah, there's another question.
What is the time scale when this instability becomes disable?
That's a good question, because what this here tells you, it's the imaginary part of the respective mode. Sorry, of the respective mode. So it means that so first of all, if it's negative, then there is no instability, because the imaginary part it pushes you back to the original solution. And if it's positive, depending on its size, you will get a growth rate like this one here. And so this means that if you're here, the growth rate has its maximum value. It grows as fast as possible. And if you go both to here or to here, so if you go very close to zero as well, so very close to, in particular, very, very small masses, the instability also becomes it's always present, but it becomes slower and slower in time. And indeed, like to see it on a computer, you should probably go somewhere close here, because otherwise you will have to wait exponentially long with a very small power.
Okay.
All right. That's exactly what you see here in this next plot. On both sides of this hump, the instability decreases in time. And here, in the two blue ones, are basically here, and you can't distinguish in which case there is an instability and in which there is not. But of course, in one side, there is a very slowly growing exponential instability. What this plot also tells you is that at least in the linearized regime, at least around that solution, the ghost is really just manifest as a linear instability, as would be any other mode. So there's nothing nonlinear, nothing violently unstable or anything that we see in the simulation. All right. So with that, you can now go through carrying that linear instability and see where it ends up. And this is super nice that now there's another group from Perimeter Institute, which has also done these type of simulations, and we can actually start to see the same thing, which is a very nice non-trivial cross-check of the numerics. And what one sees is that you can get transitions from the GR solution to the non-GR black hole. And here you see another one. This is our simulation transitioning to the non-GR black hole. That does depend on the specific initial conditions. You can probably also excite runaways like the ones that you see here if you pick different initial conditions. But that's something that we want to investigate. And the difference between the two cases is that they don't perform in 3+1, the simulations. They perform an axisymmetric reduction. We do it in 3+1, and there's still some confusion on that, I think. In any case, what we definitely know is that it can lead us from the GR branch to the other branch of solutions. And that is something that we are starting to use in simulating binary waveforms, because it gets us around the problem of producing initial data, because we can just take the GR initial data. All right, and then very shortly, if you give me 3 more minutes, I can say that we have performed simulations we're starting to perform in the last regime as well, but certainly in the first 2 regimes, whereby I mean if the mass of the heavy field of the ghost is large in this sense here. So basically the horizon mode, the mode doesn't fit into the horizon anymore. If the ghost is heavy compared to the black hole, then there are no deviations from GR in the quadratic theory. And that is a sign of the field redefinitions, because you're on the solution, the ghost is not excited, you should be perfectly in the EFT, and indeed the simulations tell you you are, even if you simulate the ghost in that way. So that's what makes it, I think, very promising to do this for the higher terms in the EFT, because if the ghost is massive enough, there's no sign of deviations here. Now, I can go to the next regime where I make the mass of the field roughly of order 1 in these units. Then I'm starting to see quantitative deviations, and I will show you a waveform in a second. And I can, of course, go also into this regime where I make the ghost very light. Then I'm not so much in the regime of validity of the EFT without the ghost. So I'm really thinking of the ghost now as a physical field. And it's very interesting, I think, to explore this regime and to understand what happens to the ghost instability, but it's sort of a different question than the effective field theory. All right, so here, as I said, you don't see deviations, and here's the example that we performed a simulation of. We really now take initial data for a black hole binary merger. We follow the entire merger until the 2 black holes merge, and we check that once in GR and once in quadratic gravity. It's a full 3+1 simulation, and there's absolutely no deviation from the GR trajectory up to numerical noise. So this really tells you that not only is the GR vacuum a solution to the theory, but also it seems to be a physically stable vacuum if the mass of the heavy ghost is heavy enough. I think this is very important for quadratic gravity as a fundamental theory, because it means that if you make the ghost mass close to the Planck scale, which you would expect from vacuum fluctuations, well, then the infrared should look basically like GR, at least the vacuum theory. All right. And now if you start to approach this regime, which you can also understand as going to shrink the black hole to be of almost Planckian size, then you start to see quantitative deviations. You can now put in numbers, and this is exactly the number where the linear instability sets on, and that is actually where you start to see deviations. And you can now, this simulation, you can start to understand. In the beginning of the simulation, we have GR black holes, and we simulate with an instability rate according to this number here. And then the black holes grow into their quadratic gravity counterparts, and then they merge. And that all happens sort of simultaneously. So it's really sort of at the edge of the EFT validity. The black holes grow and merge simultaneously. What we are currently trying to do is have them grow first to the non-GR solution and then merge. So all of that is preliminary work. Hopefully you will soon see the respective paper on the archive. That's exactly what I just said. Stay tuned for the qualitative deviations. What I think is very nice about this is that it gives us a generic prescription and I think a feasible path to obtain such waveforms and strong field predictions more generally in effective field theories of gravity. And I think it gets us closer to really treating beyond GR theories on the same footing as GR, which I think is super exciting. And with that, thanks, and we can discuss the ghost.
Thanks a lot, Aaron. We can discuss the ghost maybe, if you can.
Yeah, sure. I mean, I can tell you what is published about it. Is there any questions up to here before I go?
Yeah, I have one question. So basically, we can safely say that the quadratic gravity can be considered as a fundamental theory of gravity if you are in this M2 RG of about, let's say, 0.7. So the graph you were showing where there was a Schwarzschild and there was an unstable mode as well. So if we are in the lower part of the graph, we are still we can consider quadratic gravity as a good theory of as good as GR, right? That's what.
So I think okay. So first of all, I want to be maximally careful now because I think with the ghost it's appropriate to be maximally carefully. What we can say is first, what I'm saying is about classical theory. So I don't know what happens if I quantize the theory. What I know is that the classical theory, the simulations strongly suggest that if I'm in vacuum, I cannot excite the ghost if the ghost is heavier than this scale. And it just really looks like general relativity. I think this is sort of a necessary condition to discuss quadratic gravity as a fundamental theory. It's not sufficient, right? Because to really have it be a fundamental theory, you would want it to explain stuff at the Planck scale and even at energies beyond the Planck scale. That's something that then you would have to think about quantization and you would have to think about what happens. I think this is still very, very interesting and promising because, for instance, I don't know if you know about asymptotic freedom of quadratic gravity, but it turns out that the couplings of the theory, the alpha 0 and the beta 0, they can scale to asymptotic freedom, so to 0 values at very high energies. And if you go back to the definition of the mass, this means that the respective mass has become larger. So it's kind of a possibility, I think, now that as you scale to asymptotic freedom, you make the effective masses larger and larger, and therefore you make the effective theory more and more stable. That's something that I think is promising. But
but your graph also had a Planck scale there. So depending on how much of the Planck scale you have reached, so we can consider that as a good theory of or good theory of gravity, right? So
as a good effective theory, yes.
Yeah,
that I
right,
would
right,
attest
right.
to. Yes.
So unless you excite the ghost, the theory is all right. I mean, that's it, right?
I think so, yes. But it's also kind of a boring theory beyond GR because it just looks like GR. I mean, I think this is exciting because of the high energy behavior, but otherwise it just looks like GR.
So do you expect such kind of behavior beyond quadratic gravity as well? So the way that
it looks like GR, or
yeah.
No, I don't. And in fact, you can. It surely does not, because if you add the cubic terms, then it is no longer. So here I've shown you these two branches of solutions, right? And the Schwarzschild black hole is a solution of quadratic gravity. It's not a solution of cubic gravity, because now there's there's an invariant with Weil invariance, and that's non-vanishing on Schwarzschild, and therefore it's not a consistent solution. So I think the way that this will go is that the cubic corrections are the leading seeds of modification. And then it's not clear to me whether you have to take into account the quadratic ones to properly understand everything. But the cubic ones certainly seed the leading vacuum modifications.
Okay, thank you.
That is in line with Bueno and Cano's prediction.
Exactly.
Right?
That is in line with the field definitions and the prediction by Cano. Yeah, exactly. Which is actually nice. It's sort of, yeah.
Can I ask a question now?
Yes.
Yeah. So it appears that the well-posedness problem that you described so well is it is possible that it's applicable only in certain regions of the initial data. Initial data itself changes because if you have higher derivatives, then you are changing the initial data space itself. So in some regime of some portion of the initial data, you can get a well-posedness problem with the appropriate stability within the period of interest. Is that correct? That's how I understand.
It's correct that the fact that something is well posed or not requires me to say something about the initial data. But interestingly, here in the proof, there's no limit on the initial data. So like any smooth initial data will be locally well posed.
So the next question is that I'm going to ask is related to that, in the sense, since the effective theory has many more terms to deal with, in terms of practical advantage, what advantage do I gain by adding more terms?
By adding more terms in the EFT?
In the EFT, yeah.
So I think that what we really just need at the moment in terms of constraining physics beyond GR with the EFT is the leading terms. So because like these should capture the onset of deviations. And so I think what's interesting is to understand either in non-vacuum, so for neutron stars, the quadratic terms, and understand in vacuum the cubic terms. And then there's another subtlety, because the cubic terms, there's an argument which might also have loopholes that they are in violation with unitarity. So if that is true, then the quartic terms would be the leading ones. Then actually I think it's very unlikely that we will ever observe any deviation. But that's, I think, the terms which are the relevant ones. Proceeding to higher and higher order is not so interesting for the question of physical observability in terms of waveforms. It's very interesting in terms of the high energy limit, I think.
Okay. Thanks.
All right, I'll go to the last slide, but feel free to ask more questions.
I have a question.
Yeah.
Hello. Yeah. So this is in relation to what was asked before. Like when we include higher order corrections to the action, does that in any way change what happens on the Cauchy horizon? Like we know that we cannot extend solutions to the Einstein series equation beyond the Cauchy horizon as weak solutions. So does adding this higher order terms to the action change the regularity of the solutions that we can have at the Cauchy horizon?
I think this is related to the question of whether the Cauchy horizon eventually comes with large curvature. If the answer is no, and you can form Cauchy horizons at arbitrarily weak curvature, then you cannot say that with higher derivative terms. And I think this is a very, very important question for general relativity, in the sense of, can I have physical initial data and produce a Cauchy horizon and understand that that Cauchy horizon either lies at growing curvature or not? So think of, like, if you go into Kerr, if I make the Kerr solution arbitrarily large, the inner horizon, the Cauchy horizon, can be at arbitrarily weak curvature. So in the Kerr solution, the answer would be that can happen. But I think the interior of Kerr, it's unclear to people, to my best of my knowledge, whether the interior of Kerr, in the sense of the Cauchy horizon, forms in that way from realistic collapse. So it's just an open question to my knowledge, whether the Cauchy horizon is physically unstable enough so that it will always generate a curvature singularity. Then this can definitely change that behavior, or not.
No, I mean, even if we do not have a curvature singularity, say the singularity is a weak null singularity, that we can extend the metric continuously, but it will not have square integral Christoffel
That's right.
Yeah,
that's right. But the question whether it comes with high curvature is important for whether the local effective field theory that I was presenting can change that fact. Because if it does, if it has a curvature divergence as well, then the EFT will surely completely change the solution at that Cauchy horizon. So maybe there is no Cauchy horizon in the EFT. But if it does not, so if you cannot continue the first order derivatives of the Christoffel symbol across the horizon, across the Cauchy horizon, but it does not change the fact that the curvature is weak, then all of these EFTs will not help you. So as I said, I think it's one of the very important open questions in GR. All right.
Thanks.
So let me just very quickly say what I wanted to say about the ghosts, but stop me at any time if I'm going too far over time. So what we know currently, really strictly know, is about point particles, which is of course something wildly simpler than the field theories that I've been showing here. But it already, I think, tells you that a lot of statements have to be more cautious. So I often hear higher derivative theories are unstable. That's clearly an imprecise statement. The more precise statement would be all non-degenerate higher derivative, and now I'm restricting to point particle theories, exhibit runaway solutions. That statement, in fact, is also not correct, but that's subtle why it's not correct. So there's now counterexamples to this, and the key difference of what Ostrogradsky actually proved to this statement that is not correct is that Ostrogradsky doesn't make any statement about physical stability. Ostrogradsky just makes a statement of the Hamiltonian being unbounded from both sides. And it's physical intuition that leads us to say that if a Hamiltonian is unbounded from above and below, well, then it must somehow excite a runaway. So even for the point particle systems, it turns out that that's not always true. So you can find specific systems, if you tailor them in a certain way, that have a Hamiltonian which indeed is unbounded from above and below, as Ostrogradsky proved, but they are nevertheless globally stable. And this is an example. This is, to my knowledge, the first example here in a paper by Cédric Defayet and collaborators, which is now, Cédric is in Paris as well, which is part of the reason why I'm in Paris, they can be nevertheless globally stable, by which I mean that any initial data remains in a finite phase space volume. And I'm not going to take you through the details, but you can construct even polynomial theories which have the right structure, which are integrable. That's crucial for us being able to perform the proof. And then I'm just going to show you such a phase space plot here. You can actually convince yourself numerically, but you can also just really prove it. Since we have integrability, we have another constant of motion, and we can really contain the phase space by the constants of motion in a finite phase space volume. Now, I think in terms of connecting this, because it's interesting, it tells us that there's clearly some room for theories which have a Hamiltonian, which are unbounded both from above and below, but are nevertheless stable. Connecting that to the numerics that I've showed you all throughout the talk, I think has a bunch of steps in between. One is the big question whether integrability here is important. And I think the work that I'm citing here starts to suggest that it's not necessary, at least for long-lived motion. And then the other big thing is going to field theory extensions. And of course, I'm not saying anything about quantization. So the field theory extensions, we're actually trying to start to systematically understand that in two-field models of scalar fields. And hopefully, again, you will soon see a respective paper. And I think then it becomes really closer to the simulations that I've shown you. And I hope we can understand then in which regimes and why the quadratic gravity simulations are seem to be physically stable for certain initial data from the scalar field examples. That's sort of what I hope to achieve in the next year or so. All right.
Great. Thanks a lot. So if there are a couple of few questions, Sham, please go ahead.
The statement that in the Hamiltonian is unbounded below, physically one expects it to be unstable, is to a statement that if, for example, perturb, there will exist some choice of initial data for which the solution will be run away. Not all initial data will be run away solution. So certainly, if you have really conserved quantities, then of course it doesn't have to be run away.
No, but here really the statement is any initial data will remain in a phase space, in a contained phase space volume, and it's proven.
So it is with the certain conserved quantities.
Sorry, say again.
Is it with some certain constants of motion, conserved quantities? Because that
will so here.
Space.
No, it will not reduce the phase space, right? The fact that you have constants of motion doesn't reduce the phase space.
No, not reduce. It will constrain the motion on the submanifold.
That is right. That is right.
And if that submanifold doesn't contain the, say, R equal to 0 kind of place where one will have a runaway solution, then of course you will not have a runaway solution.
So I'm not exactly sure. So it does constrain the fact it constrains the motion into a part of the manifold. That is correct.
Yes.
It does not necessarily. So it's very hard for me. I don't think it constrains, at least not to a not self-intersecting submanifold.
Yeah.
But of course, you're right that the fact that I have integrability is important for the way that we prove things, and we haven't proven the same statements without integrability. That is correct.
Now, for example, if I change the constant of integrable submanifold, I change the values of the conserved quantities. It may happen that for one choice, it will actually go corresponding to what we'll call instability.
Yeah, but again, so this is again the statement that so you're right that like basically picking the initial data means picking the value of the constants of motion.
Correct.
That's right. But then the statement is that for any value of the constants of motion, there will not be a physical runaway.
I see. And one other small question, continuing with this. If I were to combine such a system with noise, so initial data is perturbed with some Gaussian noise or something.
Yes.
Then one possibility, there are two possibilities. Either will imply that I can always go to runaway solution, or it will stabilize the system.
Yeah, but again, so the noise will just change slightly, or depending on how big you make the noise, it will change the initial data to some other initial data. But if you've proven that all initial data remains in a finite phase space volume, then that's also true for with noise.
No, what I mean, that of course is true. As far as particular orbit is concerned, it will of course be true. But I'm saying, but because of the noise, we'll have to only take averages of the solution. And that average will never go to that. Right? So that is how the stability will come.
Yes, I think that is related to the difference between local stability and global stability. So there's, of course, also the notion that if you have a certain point in phase space, that if you perturb away from that point, for instance, by noise, or a trajectory in phase space, then you remain close to that trajectory or not.
Right.
That's a different notion of stability.
Yes.
And indeed, like we've also proven that this theory has several phase space points which are locally stable.
Okay.
I think time for last question, Shantan, then we'll end.
Yeah, so I will just ask a small question because I got disconnected in the middle. So I'm asking that when you mathematically.
Hello? Hello, Shantan. I think there's some problem with the connection. Hello?
Yeah, feel free to email me the question.
Yeah. Okay. So,
thank you very much, sir. Yeah, sure.
Okay, so we'll conclude here and we'll thank Aaron for this very extensive and very engaging talk. Okay. And
thanks for the many questions. I think it's cool.
Okay. So thanks everybody for joining in the program. So we'll conclude here.
Very nice talk. Thank you very much.
It's a great talk.
Thanks for the questions. Have a good day.
You too.
Bye.
Bye.